Hey guys, so this is the last lecture in my series for reinforced concrete design. The last topic I'm covering is the footing design or spread footing design. I covered the wall footing, I covered the single column footing, and the last one is combined footing. I'm gonna give like go over it through an example, and hopefully this will be helpful for anyone who is interested in doing combined footing, or sometimes you are forced to do a combined footing, so you have to learn how you do it. So the example we have two columns, this column and this column, and this is an exterior column. Sometimes when you have an exterior column, you have a limitation how much you have behind that column. Where is your border line? So the question here is, you have only 3 feet from the center of that column outside. After that, that's not your land. So when you have something like that, usually you try to combine this with a nearby column. So this column is a 24 by 24 square foot. 24 inch by 24 inch, which is 2 foot square. And the interior one is also 2 foot square, 2 foot by 2 foot. It's a square column. The distance between them, center to center, is 12 foot. Again, the distance from the center of this exterior column to the border line is 3 foot. The dead load, the surface dead load is 200. Service live load is 150. On this interior, service dead load is 300, and service live load is 225. So we need to design a combined footing. Q allowable from the soil report is 5,000 PSF, which is 5 KSF. The depth of the footing will be 4 foot below grade. F prime C is 4 KSI, Fy equals 60 KSI. So the first thing we do always in footing design, whether it's wall footing, whether it's single column footing, whether it's combined footing, is to calculate Q effective. Q effective is basically Q allowable minus the weight of the soil and concrete above the level of the footing, which is the self weight of the footing and the soil on top of that. So we always assume a weighted average between those of 0.125 kg per foot cube, or 125 pound per cubic foot, which is 150 for the concrete and 100 for the soil. So if I subtract 4 foot height from that, 4 times 0.125 from 5, the remaining Q effective for carrying the load from the two columns is 4.5 KSF. Now we need to locate, in combined footing, you need to locate R, the resultant. From the statics concept, I want to know what's the distance of this resultant from either one of them. So I'm going to calculate how much it's far from this distance, because if I know what's x, I can tell what's this distance, which is 12 minus x. So simple statics, to replace this two-force system with a resultant, the resultant must be equal to both of them. So basically, sum of the forces must be equal. R equal 200 plus 150 plus 300 plus 225, so it's 875. 875. The location now you need to replace two systems, you need to have the same location. So it's the moment of the resultant about any point must be the same as the moment of this system about that point. So the location will be R times X, if I take the moment here, must be equal 350, which is 200 plus 150 times 12. So R times X equal 350 times 12. And with that, X equal 350 times 12 divided by 875, which is the resultant R. That's 4.8 foot from this, and which makes sense. This column has higher load, so we expect the resultant to be closer to this column than this column. And that's R. So the length of the footing, how much the length of the footing now? So look, this is R here. That's our R in here. So we have 7.2 and 3. That's the maximum I can go from one side. 7.2 and 3. So that's 10.2. And this R, this footing must be centered about R. So it must have the same length on both sides of R. So if this is 10.2, this must be 10.2. And this tells how much the length of the footing that we are designing, which is 20.4. So we have 20.4. That's what we have. We are limited with that. And that's L. So now what's the required area is sum of the forces, the service load from the columns, which is R, divided by the effective bearing capacity of the soil. So it is 875 divided by 4. That's give you 194.4 foot square. We have the length given to us now. We determined or we calculated the length now. So 194.4 divided by 20.4. The width must be 9.5 foot. With that, we know the dimensions or the location of the resultant, the length of the footing, the width and the width of the footing. Once we have this area, so our footing will be 20.4 times 9.5. Now we go and calculate Q ultimate for strength design. Strength design and footing, after we determine the area, is finding D and the reinforcement. In footings, the first thing we find D, either based on punching in single column footing, or based on beam shear, which is gonna control the design here. You will see it in a minute. So Q ultimate equal 1.2 times the dead load. So you sum the dead load from this column and the dead load from this column, which is 500. So 1.2 times that plus 1.6 times the live load, 150 for that and 225 for that, divided by 20.4 times 9.5, which is the dimension of the footing. You get 6.2 KSF. So now we have the bearing capacity, the ultimate bearing capacity coming from the soil for strength design. So let's draw our footing and see what we have. The next step will be is to draw the shear diagram, the shear and moment diagram. So now it's a beam. This footing is a beam. So this is what we have. That's the first column. The distance, its width is 2 foot. And the distance from the center to the outside was that. So this one is also 2 foot. Because the distance to the center is 3 feet. 2 plus 1. The overall length is 20.4. The second column is located here. Maybe more, just to have symmetric. This is the second column. It's also 2 feet. The distance center to center is 12 feet. So we have 12. We have 3 from here to here. The remaining from the 20.4 is 5.4. So the distance from here to here is 5.4. So the distance from here to here is, from the face of the column, is 5.4 minus 1. So this is 4.4 feet. So that's a beam. You can look at it, a beam. If you flip it, it becomes exactly a beam. Or you can look at it as this. So now the columns are the support. You can look at this as the load is coming from here, from the bottom, from the soil, and the support is the column. So it's just simple shear diagram. And let's do it. So this is the shear V diagram. And this is in kip. Everything will be in kip foot. So the shear is in kip, the moment will be in kip foot. And again, we said this bearing capacity is 6.2. 6.2. Right? 6.2 kip per square foot. So you have to be careful. The loads here also must be the ultimate loads. The loads here must be the ultimate loads. Now, R doesn't exist anymore. R doesn't exist. R is used to center the column. So we need to know how much the ultimate load in this column, which is 1.2 times 300 plus 1.6 times 225. Gerard, can you do that? So we need to know how much this ultimate in here and how much this ultimate in here. You cannot just have R now and draw for R.
So the first one is 720.
So that's 720. Okay.
Yeah, yeah.
Mm-hmm.
And 480.
And this is 480 kip. Remember, this is the total load coming from the columns, right? This one, the bearing capacity is 6.2 KSF, K per square foot. That's only for 1 foot strip, so I have to take that for the overall width. The overall width. This needs to be multiplied by the width, the tributary width, to get it per foot. So that's how we draw the shear diagram. So the 6.2 need to be multiplied by 9.5, which is the width of the column, the width of the footing.
Right.
And this number is?
58.9.
So this is 58.9 kip per foot. So this is 58.9 kip per foot, assuming the width of the footing is 9.5. So all our values will be for the full width of the footing. Okay? So now let's see what you have. So this is going up. I'm going to draw it in red. So I have 50, I have 0 here. Then I will start as I go. At 4 foot, this is the face of the first column. And this is the face of the second column. And this is the face of the first column. And this is the face of the second column. So as I go 4.4 at an intensity of 58.9, I'm going to reach how much?
The first one is over there. You want to have the moment or the shear?
The shear. The shear now. Let's draw the shear.
Oh, okay.
So it's going to be 58.9 times 4.4.
Mm-hmm. 259.16.
So this one is 259.
Yeah, just give it 215 or 260.
We don't want to approximate a lot. We will approximate at the end.
Oh, okay.
Okay? Because there is a lot of calculation. Now look, as I cross from here to here, over the length of the column, there is the drop in the column. So the column will, before we do that, the column will drop it down over a 2 foot width. So from here to here, the column will drop 720. And don't forget that there is this also over a 2 foot going up. So you will have, what you will have in here now is 720 minus 259.16 minus 58.9 times 2.
Mm-hmm. So it's minus 343. 04.04.
That's good. 340. You keep it on the calculator so you don't sum at them. Again, this is usually there is a mistake. Usually students make a mistake in here. So you're gonna drop. You go down the reaction or the load on the column, but don't forget that the width of the column has also underneath it has 58.9. So also there is 58.9 times 2. It adds to that. Then you subtract that here. So this is okay constant. So this is linear. Then you go down to this guy in here. So as we go now over 12, I have up shear 58.9 times 12
times 10 should be
times 10. Yep, this is 10.
Oh no, that's center to center.
Center to center was 12. So this is 12, sorry. So now we go from 10 to 10. This is 12. We're going to go 10 to 10, which is times 58.9.
Yeah, that's 245.96.
The difference.
Yeah,
So you will get 589 minus that, you get to how much?
245.
245.
0.96.
0.96, which is, again, we're going to calculate them at the end. Usually at the end, you will see the moment diagram is off by 5 kip foot, which is not a big deal. Now, as I go from here to here, we have the drop in the column, but we also have this thing up. So it's going to be 480 minus 245.96 plus, which is, you add to that one, 58.9 times 2.
Minus 116.
So you go to
0.24.
116.24. Then this here, it must be, if you multiply 58.9 times 2, should go to 0.
Yeah, it gives 1.
That's what we have. Okay? That's what we have. So I'm gonna try my best now to find the location here. This is 343.04.
Yeah, 343.
Yeah. So now we're gonna construct our moment diagram. As you can see, the moment diagram here will be, this is positive, right? Up. This is negative. This is positive. This is negative. So we need to find some. Distances. So this here, from here to here, x. Let me do it in black. This from here to here, x. So x over 343 equal 10 minus x, which is this distance from here to here, over 246, let's say. So x over that equal 10 minus x, similar triangle. Or what you can do if you want, Gerard, you can do x over that, okay? Look what's equal. Equal 10, the full, over the sum of both of them.
Yeah, so that way. So we said
Equal 10 over both of them.
and both of them was it's 58. So it's
So this is 343, look,
343 times 10 over the
over the sum of both of them.
58, 9.
Over the sum of them, yep.
It's 5.82.
So this is 5.82, and this is 5.82, this is 4.2.
17.
Point
17. 176, yeah.
Yeah.
Or one 8. You can put 1 8, so it adds to 10 actually.
Yeah. So that's 1 8. So both of them are 10.
Mhm.
We need to do some small also here, you know.
That's two. That's,
Yeah, we need to do some similar triangle also for this distance from here to here. Which is usually, if you want to assume it, this is going to be 259.16 divided by the sum of them times 2.
Mhm.
How much?
The sum of them it's 70. No, okay. 1 second. .86.
This is 0.86, and this guy is the remaining, which is 1.14.
Mhm.
Because both of them is 2. Likewise here, 245.96 divided by the sum times 2, you get this thing in
And
here.
the sum is 480. So the first one it's 135. 136. Better.
136, and this is 0.66,
0.64.
0.64.
Yeah.
So we have all the dimension to draw the moment diagram. We will positive here, then we're going to be negative. So this is going to be our moment diagram.
Yeah.
So this one, to the face, this area here,
That's 4.4.
look how you do it, Gerard.
It's a triangle.
This is 4.4, right?
Yeah, times 259.6.
Wait. This is 4.4, right?
Mhm.
Add to it this one because all of this is positive.
Yeah.
So you're going to be 4.4 plus 0.86.
That's 5.26.
Times 259.16 divided by 2. I get all of this positive area because this is all positive. So I'm going to do it as one triangle because this is
Oh,
positive.
Yeah, that makes sense. Alright, so that's 681.
Here and then in the center will be
681.
681.
0.6.
That's now, let's round the moment now. 681 point.
Yeah, 682 then.
So this is all here at this point.
Mhm.
682. Remember, this is 0 here, so this is going to look like that.
Mhm.
0 and the slope is going here. Little bit will change a little bit in here. So it will go like that, then like that. You see, it's going to go like that up to here. Then it will flip and become like that within the column. Because the slope is here 0 and it's decreasing in here. Something like that. Then as we go from here to here, but again, you don't worry about what if this small tiny piece within the column or under the column. As we go from here to here, we have this area, which is 5.82 plus 1.14, half of that times 343.
Yeah.
That's negative. Minus 682.
So that's minus 511.64.
You went to 511,
Yes.
512. So there is, and this one will go a little bit like that and like that. Why like that, guys? Hopefully, this is how I teach in structural analysis. The slope here is 0, that's a 0 slope. The slope here is negative, so that's a negative slope. So it goes that way. Flat, the slope is 0, then negative here. As we go from here to here, we have this 4.18 plus 1.36 divided by 2 times 245.96. That's positive. You subtract this from it, we see where we're going to go here.
So that's 683.72.
Positive?
Yes.
The same as that one?
No, well, not the same. It's a little bit different. But it should not go. It should not go there. It should go.
To this one.
Yeah. There you go.
So this one is, you said
684. It's my approximate.
684.
Yeah. So it goes positive and then it switches.
Are you sure about that?
That's what the.
Did you subtract this from it?
1.88 plus 1.36 times 245.96 over 2. Oh, actually, yeah, you're right. Sorry. Yeah, I forgot to subtract. It's 169.
So this one will be
169.
169 in here in the column. Now this will give you 169, which is, so the moment diagram will close. So 2 plus 2.64 divided by 2 times 116.24. This, usually there is like 1 or 2 kept off.
Yes, it's more than 1 keep up actually.
Yeah, that's fine. That's absolutely fine. You will have 5 kept foot, something like that. More?
Yeah, more.
153?
Like
There's
that.
something wrong.
Yeah.
Here, wait.
Let's see.
So 245.96 times, did you add those 131.36 to that?
Minus 512, right?
Minus 512. How much?
That's 169.3. I mean.
Then this one is not that much, Gerard.
Yeah, I know. Like there's a.
2.46 divided by 2 times this number is this. 2.64 divided by 2
Yeah, I did that.
times 116. Oh yeah, you mean the difference is like 10 kept foot? Yeah, that's absolutely fine.
The difference is 10. It's not 1
Yeah.
3.
Yeah, usually you have off something like that. So, but that's the moment diagram. Okay, so this piece here, see we have this positive here. So the reinforcement must be bottom up to this distance from here to here. And this reinforcement, on this segment here, the reinforcement must be at the top. So this reinforcement must be at the top. This needs to be calculated, how much the length, and usually we extend it a little bit within the column. Then this one is a cantilever, so the reinforcement at the bottom, and this tiny piece also will have a reinforcement like that. So the reinforcement at the bottom, top, bottom, as you can see from the moment diagram. Now we need to calculate, before we go there, the reinforcement is easy to calculate once we have D. So now we have D. So the ultimate shear is, we have this 343. We have this 343 at the face of this column. We know the critical section for the beam shear is at D from the face of the support. The critical shear will be at D from this. So this is the face of the column. At D from here, that's the location of the critical section. We know the slope here. So if I know how much D here, I can calculate V ultimate there, which is V bar U, as we studied. Then I can calculate, check the shear. So we're gonna assume D. So we're gonna assume D. I'm gonna try to work things out here to make sure we have everything. So how much I'm gonna assume D? So 480. This is 200 and 150. So assume this is a major footing, as you see, a major footing. So I may assume D equal 2 foot. D, or if I assume the overall depth of the footing will be 3 feet, so which is 36 inch, and we know we subtract usually 4 inch to the center of the steel. So that's usually, if let's go with D equal 32 inch. D equal 32 inch. If D is equal 32 inch, this D here is how many foot?
It's 1 second. It's 2.67.
2.67 foot. 32 inch divided by 12 is 2.67. So V bar U equal this again. It will be here because this is the maximum shear. If this one was more or this one was more, we do it here. So it's going to be 343 minus the slope over this D. So it's going to be 343 minus 58.9 times 2.67.
And that's 185.
V bar U is 185.7 kip. So this is V bar U. Now what's VVN? For the beam shear. This is a beam shear, not punching. This is not punching. This is a beam shear. V bar VVN equal phi 0.75 to square root of prime C BD. Good. For punching is different. It's phi, which is 0.75 times 4 square root of prime C times B naught D, and that B naught is the parameter for the punching. So phi VN equal 0.75 times 2 square root of 4,000 times B. What's B now? B is the 9.5 times 12. It's the width of the footing. Everything is calculated for the full load. So this will be times 9.5 is times 12. How much?
Oh,
9.5 times 12.
114.
So it's 114. That's 9.5 foot times 12 times D is the assumed 32. We're trying to check if D is good or not. And this is in pound. Usually once you have this one under the square root in PSI, the answer is in pound. So you divide by 1,000 to get it in kip. So you compare it with this one.
346.
So this is VVM equal 346 kip. This is high kind of. This is high. So what I'm gonna do, I'm gonna drop D. I'm gonna drop D. Remember, when you drop D, this will drop, this will increase. You have to be careful. So that's how you do it, trial and error. So I'm gonna assume my footing will be 2.5 foot, which is 30 inch. You know, we can try 2 feet.
All right.
We can try 2 feet depth of the footing. The footing will be 2 feet. So D, which is 24 inch, D will be 20. So if we can do it fast, V bar U will be 343 minus 58.9 times 20 over 12.
That's 244. 245.
So if you do 2 feet, you get 245 for V bar U. And this here will be 20,
Yeah, so
which is basically this answer.
346.
This answer times 20 over 32.
Not good. 216.
So this will be 216. No good.
So it's 30.
So again, we're gonna increase it. I'm gonna make my footing 30 inch, 30 inch, which is 2.5 foot. For that case, D will be 26. So D will be 26. You divide by 12 to get it in there. So you get V bar U is how much?
215.
So that's 215.
That's right.
V bar U, if we take D, if we take H, 2.5 foot. The thickness of the footing is 2.5 foot, which is 30 inch, minus for D, minus 4 inch the cover, you get 26 inch. And this will be
280. 281.
281, okay. Okay.
Yeah.
Okay.
Sorry.
It's a little bit bigger than that, but that's fine. They're gonna save you some steel. It will save you some steel if you increase D. If you want to drop it a little bit more, that's absolutely fine. Especially when you work with the metric system. If you are finding this in centimeter, you have work. But usually we like to have the thickness of the footing going by 3 inch increase. So you can maybe drop it down to 27 and check. The overall thickness is 27 inch, which is 2 foot 3 inch. But this is okay for me. I will do it this way. So now this is D. After that, you need to check the punching. I will show you how you check the punching. Punching usually will be fine. Punching will be fine, but I will show you how we check punching. Remember, the maximum moment we have is 682 here, negative, and 512 here. I'm going to show you one design, how we design for the 682, and it's for you to continue the rest. But let me show you also how you do the punching, and you can do it on your own. For the interior column, it controls. So that's your footing, the plan view of your footing. So this is your interior column. Okay? This is your interior column. What's the loading on this one? Was
4. Oh, 3 is up there.
7, the maximum, the factored.
Oh.
720?
720, yeah.
So it was 720 kept. This is the loading. For punching to occur, we assume it occur on D over 2 on all sides. That's the punching parameter, P node. Okay? If this one is punched by itself and the other one you assume it's punched by itself. So we'll see how much area you have. So the column is 2 feet, which is 24 inch, right? 24 on all sides. And D we said is 26 inch. So this one is,
50.
you have D over 2 from here and D over 2 from here. So 24 plus 26, which is 50 inch. So B node equal 4 times 50 equal 200 inch. It's 50 plus 50 plus 50 plus 50. Okay, that's what's resisting the. Well, that's how the failure piece, if this column punched through the footing. So now what's V? What's VU on this one? VU for punching is equal the load on the column. Is equal the load on the column minus the resistant, the bearing capacity on this area. So the 50 inches is how many foot?
The 50 inches?
Divide by 12.
It force 4.17.
17?
Yes.
4.17. So the soil is resisting 6.2 times 4.17 times 4.17. So VU will be 720 minus 6.2 times 4.17 times 4.17. So VU is
612.2.
612.2 kip. That's how much the resistance must be from the punching shear, which is VVN equal 0.75 times 4 square root 4,000 times B naught, which is 200, times D 26. All of this is over 1,000. So
that's 987.
So that's 987 kip. Way bigger than that. Punching is good. You have to check punching also for the second one. It will be fine. The last step is to design the reinforcement for these moments at each location, and you should know where to put them. So for M ultimate, how much? You said? For the at the bottom of the first one.
682.
682 kip foot. Okay. So we make this one equal phi mm. So 682 times 12 to change it to kip inch equal 0.9 R B D square. Okay. So R equal 682 times 12 divided by 0.9 times what's B now? Is the full width,
9.5,
which which is 9.5 times that, which is 114 inch. 9.5 foot times 12 times D is how much?
26 inches.
26 square. You do that.
You may want to put 12,000.
12,000 to change it.
If not, it's not going to work. Yeah, there we go.
Yeah, it has to be in PSI. This is in PSI. So how much?
118.
118 PSI. You go to the design aids, if you want to do it, to calculate the required rho for that. And you will realize that this will be smaller than, I think, rho minimum. So rho min
Way smaller than that.
equal 200 over 60,000, 200 over Fy, or, which is 0.0033. So for this row from the table, you will find something very small.
Yeah, it's 0.00. 118 is right. Yeah.
1.8,
0.002.
0.002. And our row minimum is 0.0033. Most of the time in footings, guys, row minimum control for the reinforcement, because D is determined for shear, no stirrups. D is big, huge, the depth is big to resist the shear. So in this case, the reinforcement must be area of steel equal 0.0033 times B is the full B, 114, times D, 26. As
It's 9.78.
9.78
You can use 10 9.
inch square. So you can pick 10,
Number 9.
10, number 9. The area of number 9 is 1 inch square. This will give you 10 inch square, or basically what you have is typically almost 1 every 1 foot.
Yeah, you can just.
Okay? You will have 10 bars over a 9.5 width. You subtract the cover from here and the cover from here, so it's almost that. But the guys will distribute those 10 equal distance from there. You can do the design again for, if this one requires the minimum, it means everywhere is the minimum. If this 682 required the minimum was less than the minimum, for the same D, the minimum will be everywhere. The minimum will be everywhere. Remember, this is structural. This is structural. Raw minimum for it is 200 over Fy, or 3 square root of prime C over Fy, which will be 0.00332. So this controls for the minimum. Okay. One last thing you do it on your own is there is one more thing need to be done. See this column? Of course, you need to detail all your calculation. We, in the other direction, there is something, it's called transverse beams. Those transverse beam. We assume there should be a strong beam under the column over a distance D over 2 from here and D over 2 from here. That's the width of the beam.
B naught.
What?
It will be B naught.
Same as B naught?
Yeah.
For the bunching, you mean? Yes.
Yeah.
So this one will be D over 2 and D over 2, and this is 2. This will be 50 inch, the width of that beam. We assume this beam, if you look at the plan view, that's your column. This beam is supposed to provide, it act as a cantilever at the face of the column. It acts as a cantilever at the face of the column. So there will be a reinforcement at the bottom in here, special reinforcement in the other direction to resist this thing. The arm for that will be, this cantilever arm will be 9.5 minus 2 divided by 2. 9.5 is the width, minus 2 is the width of the column, divided by 2 to get that. So this is
3.75.
3.75 foot. Okay? And the load, remember the intensity is 6.2 over 50 inch, which is 50 inch we said is how many foot?
50 inch, it's 4.17.
So the 50 inch equal 4.17 foot. So the distributed load on this one,
25.83.
so the intensity of the distributed load Q ultimate on that thing over the tributary width equal how much?
25.8.
25.8 kb per foot. So ultimate equal Q ultimate times this cantilever length squared, which is 3.75 squared over 2. This will give you ultimate equal
181.64.
182 foot. Remember, D for this ultimate is the same as D, but B is 50. So if you do that, remember there is steel at the bottom. By the way, D could be something smaller even if you want to subtract 1 more inch, because the main steel will be at the bottom.
Oh.
So our steel will be that.
Use 25 then.
So we will use D instead of 26. We will take 1 more inch to the center of this layer of steel because this layer is at the top. So D will be 25 inch, B equal 50 inch. So R equal, ultimate is 182 times 12,000 divided by 0.9 times 50 times 25 square. This will give you in PSI R.
So the R is 77.65. So it's a smaller.
This is small.
Yeah.
This will be less than
0.003.
0.003. So you use reinforcement in here equal AS. So row minimum will control. If you go to the design aids, this will be less than, will give you row less than row minimum, because we checked it for something higher than that. So AS will be row minimum 0.0033 times
50 times 25.
times 50 times 25 equal
4.12.
4.12 inches square. You can use, let's say, 5 number 8. I'm not sure if they're gonna do it or not, or 6 number 8. Maybe they can do it. But you pick steel to provide you something more than that, and this will be in this area here. This will be like act as a beam. And for this one, it not necessarily to be the same, but look, it will be the same. You know why? Because it's determined based on the minimum. But the moment here is different, remember. Actually, it's not different. It's the same. So it will be the same under both of them. It will be the same under both of them. This is your transverse beam in the other direction. This is your transverse beam in the other direction. Okay? Also, in these locations, when we don't have any steel in the other direction, we provide for this steel here, this steel here is non-structural in the other direction. And some in here, we provide shrinkage and temperature. Shrinkage and temperature, and draw for shrinkage and temperature is 0.002 for footing. So you do 0.002 times, if you calculate per foot, how much you need per foot. So it's going to be 0.002 times D is D what you have, which is 26 inch times, times H, which is 30 inch. Okay, raw minimum, AS calculated from the raw minimum or for raw shrinkage and temperature is multiplied by BH in footings and in slab. So you do that 0.002 times 30 times 12. You calculate area of steel, you pick number 4 or number 5 at 12 inch, or you can go up to 18 inch, which is 1.5 foot. With that, again, there's so many things you need to do. The drawing, it's a major footing, but once you understand the fundamental of designing one of them, you should be okay to design any combined footing with any constraints. Sometimes you are limited with the width of the column, so that's why you are forced to combine both of them. Sometimes you don't have a requirement behind one of the columns. You just have a limitation or constraint on the width. You cannot have more than 6 foot. So you are forced to have very long combined footing. Okay, so that's it for the reinforced concrete design. Hopefully in the future I will be able to have like structural analysis, statics, and steel design. And thank you for watching all of this. And I would like to acknowledge Gerard. He's one of my best students actually. He's graduating and going to Spain. He's a Barcelona fan actually. So, and thank you so much guys for watching, and see you in another lectures.